All right. Good morning, everybody. Welcome back to Motion Planning, now lecture 7. Last time, Andreas talked a lot about tree-based planning. So we looked at RRTs and the properties of it. So one important property was probabilistic completeness, which means if a solution exists, we will find it under the assumption that we just run our algorithms basically forever. And we also looked at asymptotic optimality. So if we now introduce some sort of cost function into the mix, and we are interested in not just finding a solution, but the solution that minimizes that cost function, then we have shown that the RRT itself is unfortunately suboptimal, but that we can extend it with a small trick called rewiring in order to make it asymptotically optimal. And then also last time for these cases, there were a few theoretical insights on how these properties can be proven. So in particular for the probabilistic completeness, it was some sort of induction-based proof where we had the proof mostly in pictures with little balls that we show can be connected. And then for the proof of asymptotic optimality, we also have to, in addition, ensure that the sequence itself is correct, not only that we can connect it in any way. And then also Andreas discussed a few more like advanced extensions of these algorithms. So in particular, informed RRT star, where it combines ideas from informed search with RRT star, and one very concrete instance, which was bit star. And so today, basically, we have kind of two major topics that I have in mind. The first one is that we kind of extend this whole idea of tree-based planning in geometric spaces to the kinodynamic case. And we look at many different algorithms to do that. And then the second part, if there's still time, then we look at some more advanced geometric planners, not some tree-based, some not tree-based. And if there's not time, then we move that to in 2 weeks. Okay, so let's start with optimal kinodynamic planning. So just to recap, since we have been the last few weeks or so mostly in geometric planning, the motivation of kinodynamic planning is that not in all robotic cases we can really rely on just planning a path and then being able to follow it. So if you think about these examples, like a race car or a more or less autonomous boat or a drone or anything for planetary exploration, then we have fairly complicated physics behind that constrains the motion that we can do. And even if they don't constrain the motion, like for example, a drone can really fly discrete paths, it might constrain optimality. So it's typically not optimal to fly these sort of discrete paths. And so in kinodynamic planning, we had this following formulation. So we still have a state space and a free state space. Sometimes we also said we had kind of a workspace and this mapping function that tells us how to map from the workspace or from the obstacles into from the states into the workspace, and then if we have obstacles in the workspace, we can check collisions there. So that was an alternative interpretation. We have our control space U that just tells us how our robot can be operated. And then we have this dynamics function that is typically also given. Sometimes it can be learned, but that more or less tells us over time how our robot moves. And then given some start state and some goal region and some cost function, we are interested in finding a trajectory. And what a trajectory actually means is it's a sequence of these configurations that should be all collision-free and also actions over time. So in other words, it's like this function that maps this input parameter time to this configuration and state space. And then we can ask these two questions, like if you're just interested in A solutions, and it's a feasibility kinodynamic motion planning problem, and then we just compute A trajectory, and then if we care about optimality, then we also want to find from all these possible solutions one that minimizes the cost function. And there could be multiple, of course, but we want to have one of them with the lowest cost. Okay. And so let's first kind of dive into the principal approach, how we can use tree-based, sampling-based algorithms to solve these sort of problems. And then after we looked into that, we kind of study 3 more concrete algorithmic examples that follow this pattern. And then we have kind of a 4th method that doesn't exactly follow the pattern that we also consider. Okay, so let's first start with general variance. So the first thing to consider is that there's kind of, generally speaking, 2 ways you can deal with this dynamics function that you have. The first one is known as steering, and the second one is known as forward propagation. Maybe I start with forward propagation because it's kind of easier. It's also what you have already done basically in programming assignment 1. So let's assume you're given some state and some control and some kind of time difference delta t. Then to compute the next state, you basically just query that dynamics function that you have. You might need to integrate it. You can use Euler integration or something else. And then with that, you compute the next state. And what's kind of nice about it is that with all the information we're given, with a little bit of math, we can just do it. And it's a pretty basic computation. The downside is that it's pretty unclear how we can use this sort of simple propagation for planning, especially if we want to do the planning efficiently. And so an alternative approach is what is sometimes known as steering, sometimes also more known as connect. And here the idea is, let's say we are given 2 states, and then we want to just somehow magically, automatically compute how we can move from the first state Q to the second state Q prime. And that by itself actually means we have to solve a kinodynamic motion planning problem. So it's kind of almost like a chicken and egg problem. Depending on the system, like for simple systems, there's actually closed form solutions for this. For other systems, it's very tricky, and you use more numeric approaches or optimization. Now, what's the advantage of the steering function is that it basically allows you to just use any of the geometric motion planners that you have learned. So in fact, instead of using this sort of interpolation that we have used sometimes to connect or move in the direction of kind of states, we would now just query the steering function and everything else works out normally. And so even things like RRT star with the rewiring would just work, so we would get asymptotic optimality. And indeed, if we have a closed form solution to solve these sort of problems, and the closed form solution is efficient, that is what many people would do. But generically, that's not possible. And so the other way is to use this forward propagation. And so we kind of look today at some algorithms that kind of use forward propagation for the motion planning. Okay, so how does it look like? So here's some pseudocode for the meta algorithm, and then as I said, there will be like 3 concrete instances of that algorithms that we see today. So we are given a start state, a goal region, our state space, our action space, our dynamics function, and some propagation time for the dynamics. Then as before, we just initialize our tree with the start node, and then we kind of follow just 3 basic steps. The first one is we select some sort of node in our tree. The second one is we call our propagate function that just moves somewhere, starting from that node. And then if what we selected and the new state we reached were successful, then we can add the connection. Okay, and then this, of course, is an algorithm that only cares about the existence of the solution. There's like no real cost notion here right now. So in practice, because it's this probabilistic completeness property, we just would run it until we find a solution, or maybe after some finite number of iterations, we would just kind of give up. Okay, any questions high level on that? No? Good. Then let's look at kind of the different alternatives we have. So for node selection, for example, we could just use uniform selection. So let's say we have a tree that has already 5 vertices. Then we pick each vertex with a probability of 20% for expansion. We could have some sort of exploration first. That is what you typically find in RRT itself, because there we had this Voronoi bias, and the idea of the Voronoi bias was that we want to kind of benefit exploration. So we would always pick whatever vertexes in the tree where we believe we should expand more in that direction. And then lastly, we could also try to use this sort of optimality framework where we say whatever we think is kind of a node that seems to be close to a solution path or on a very low cost solution, we try to pick that. Then for propagation, there's also at least 3 methods. So maybe the most simple one is that we randomly sample some control action. We use our fixed t prop time that is typically user provided. Then we apply it with the dynamics, we compute the next state, and we are done. Monte Carlo means we now not only randomize the control itself, but we also randomize the time, how much we want to forward propagate. But then we keep kind of the control constant. And then we just propagate the system forward. There could be also a variant where kind of for all the like fixed little time steps, we randomly pick different controls. So we do a little rollout similar to like a Monte Carlo tree search. And then there's a kind of more of a shooting method or a guided Monte Carlo tree search method. And that one just repeats the Monte Carlo method k times. So for example, 10 times. And then it looks at all of the kind of resulting states it got and just picks the one that is best with respect to some metric. And we see one example later And then finally, we have to decide if we actually want to keep whatever connection we made or not. And then the most obvious one is, okay, we tick it whenever it's collision free, and otherwise not, because it's not part of the solution. And the second version is that we also take the cost somehow into account. Okay. And then we can basically use different combinations. So we had like 3 things. Each of these 3 things had 2 or 3 options. So there's quite many combinations that you could do. And we just look at kind of 3 of them, namely kinodynamic RRT, naive random trees, and stable sparse trees. Okay, any questions so far? Good, so kinodynamic RRT. So here we have the following combination. We basically say we select the node using the exploration first. So in other words, we just use the normal Voronoi bias that we had from the traditional RRT. Then for propagation, we use the guided Monte Carlo. And then for the add connection, we just use very basic collision checking. Okay, so let's look at an example. So let's assume we kind of already have a tree that has these sort of nodes in here. Then the selection procedure would do what exactly in RRT? So how would you now figure out which node to select and how to grow your tree?
First generate a random point, and then find the nearest neighbor, and then try to step forward a small step.
Exactly. So we sample that random point. We find the state that is closest with respect to some metric, so far as everything is the same. And then kind of the new thing is this propagation, and we said it's guided Monte Carlo. So what that means that we first now sample some control and some time. And let's say in this case, we ended up somewhere here. And then we repeat the same procedure. So we again start at that near state. We sample something else. And then maybe we end up here. And we repeat it again and again and again. And this k is typically a user-provided parameter. Usually not too high, like something between like 5, like between maybe 3 and 10 or so, not much higher. Depending on the dimensionality of the system also. And then once you have kind of your 5 choices, you pick the one that is best. And then what would be the best one in the RRT world in this case?
Probably the middle one, which is closest to the random one.
Exactly, because in geometric space, remember what we try to do is just kind of connecting them directly or moving with a fixed step size. So here we take just this one. And then we are done and we kind of repeat. Okay, I guess, yeah, I forgot we have to first check then at this point, is it actually collision free? This example was collision had no obstacles, so yes it is, and then we're done. And what's kind of cool is that kinodynamic RRT also has this nice same property that RRT had, namely that it's probabilistically complete. There's a little star, but that doesn't matter today. We will revisit that in 2 weeks, what the star actually means. So does anybody remember how the proof works for RRT? For probabilistic completeness? too difficult. Okay, then we will revisit it again, but kind of on a very high level, the proof idea was that we assume there's some path, that is the solution. We cover the path with these little balls, and then we basically say, okay, it's an inductive argument. The first ball we can reach for sure because that's the start state. And then by induction, we just assume, okay, let's now assume we can reach some ball on that path. And then the induction step is that we have to show that we can reach the neighboring ball also by connecting it. And then on a very high level, we basically show that this probability of at some point sampling something that reaches that next ball is non-zero. Right? And so would that proof work here as well? Yeah.
Well, I could think that maybe it doesn't because it depends on what actions we can do. So again, if we can only do a straight line, we can never reach some states which are not on that straight line.
Exactly, yeah. Like we can imagine we have like a dynamical system that can only move in like very constrained directions, and it's really not intuitive that this connecting balls thing would ever work. And yeah, also this proof doesn't work in crazy cases, so it makes us assumptions about what the dynamics can do. And specifically, it looks at the small space local controllability property that I have to introduce first. So in the geometric case, imagine you're in state here. Then you can basically reach anything on the sphere because you could just go anywhere in any direction. Also, if you remember, earlier we discussed kind of the equivalence between kinodynamic and geometric planning, and there was one particular system that made it equivalent, which was the single integrator. And also in the single integrator, you can always find an action that moves you in the right direction to go basically anywhere. Now in a kinodynamic system, you might be more limited. So if you look at, for example, your unicycle, your car example, then if you have a specific heading, like you're here and you look more in this direction, then you can't really go backwards, right? You can at most maybe do a slight left turn and a slight right turn. And then what a small space local controllability says, okay, if we have now our state Q and we want to maybe go to some other state Q prime that's within the vicinity of that Q, then there should be a bounded but potentially larger region with this radius that we need to cross to get there. Right? So, for example, if we have a dynamic system that allows us to do something like that, that would be small space local controllability. And so we have these kind of two parameters. We have this local epsilon, which is the epsilon neighborhood, and then we have this delta, which is this larger area in which we can go. And then now thinking back on the argument of balls, what should be the size of the balls here in order to make this sort of argument? Yeah.
It must be at least the size of the white circle, because at least the white circle must be infinitely at all times, right?
exactly, because otherwise it might be difficult to reach. Yeah, so again, in these little fun pictures for the series of Ball's argument, so let's assume we have some solution trajectory from the start to the goal, and we just see kind of some portion of it here, and those are samples on this example trajectory, and we have already grown some existing tree, like marked in the green color. Right, and now basically with a series of balls, we can draw the balls around it here. And the question is, let's say we at some point reach by the inductive assumption of one of the balls, then we have to show that we can also go to the next one. And we can now use this small time local controllability argument by saying, okay, as long as these are just epsilon apart, then there's this sort of delta region where they are guaranteed to be connectable. And if they're connectable, there will be at some point a probability that's non-zero, so it actually finds this path. And then there's a few technicalities about kind of the sizes of all these different balls, like how big they have to be in order for the math to work out. But kind of the nature of the argument doesn't really change by that. Okay, any questions about probabilistic completeness for kinodynamic RRT? Then I have a question for you. Is kinodynamic RRT also asymptotically optimal? Yeah?
Well, wasn't RRT itself not asymptotically optimal? Like only with extra roots, I would argue this is also not asymptotically optimal.
Exactly. Yeah.
If we don't do anything extra.
Exactly. And doing the extra step here is difficult with the propagation because in RRT we went to RRT star. RRT star, it's a rewiring, but for rewiring we need this connect or steering function, which we might or might not have, depending on the dynamical system. Okay, so that brings us to a method that is actually asymptotically optimal, but rarely used, and we will see why. But it's still good to study before we study something that's actually used and also has good properties. Okay, so it's called naive random trees. It also already tells you why maybe it's not used that much, because it's too naive. And it is another instance of this meta algorithm I talked about at the beginning. And we now have to define what we do. So select node changed to be uniform. Propagate node changed to be non-guided, but still Monte Carlo. Or you can think of it as guided Monte Carlo with k equals 1. So that's then the same thing. And maybe add connection actually is kind of the same. And then the pseudocode is quite simple based on these things also. So we first do this uniform sampling. Then we do this basic Monte Carlo propagation based on the node we have found. We just go in some random direction because we don't have this sort of Voronoi bias here. And if we are collision free, then we just add it to our tree. Okay, so in pictures we have the same graph here. Uniform selection now means I have 1, 2, 3, 4, 5, 6 nodes. I pick each of them with equal probability. So in this example, let's say we just pick this one. And then I do basically k equals 1 like before. So I just sample some time, I sample some control, I forward propagate, then I would end up here. Then I check, is that collision free or not? And yeah, then I'm done. Okay, maybe fun question. What is so we call it uniform selection, but is it truly uniform?
It's probably just random sampling without a bias. So it would be spread out across the whole field, but still random.
Yes, but it's you sample actually a discrete number. So you have, if you have these 6 nodes, it's really just a number between 1 and 6, not like real numbers. Right? Yeah.
I would imagine that if we run this multiple iterations, that the nodes that are there in the beginning have a higher chance of being selected again.
Exactly. I mean, the best example is a root node, right? Like in the first iteration, it has probability 1 because there's only one node. And the second iteration, it has probability 1/2 and so on, right? So it's actually always much more likely over multiple iterations to pick the root nodes than any other node. Yeah, but so each step it's uniform, but then over the sequence, maybe not so much. Okay, and the kind of the crazy thing now is, I mean, this seems even simpler than kinodynamic RRT, right? And yet it has this funny little property of actually being asymptotically optimal. Can anybody imagine why? Mm-hmm.
I think because we always sample randomly any of our nodes, we will at some point sort of connect the ideal path from the root node to the sort of next smallest node on the ideal path, and if we run it long enough, then at some point this ideal path will exist, but like of course after a long time.
But why was it not the case with regular RRT? What is like the difference here?
Like I think the problem is that like with regular RRT, we might initially have an suboptimal path, but like this will never get corrected, right?
Exactly. So I don't know if we had an example, but basically for the original RRT, the Voronoi bias that helps us exploring also sort of prevented us doing anything optimal. Right, so maybe I do a more extreme example. You have something here, and maybe that's your start node, that's your goal node. And then whenever you sample something that's close to the goal, you will always connect it to this. And then you have this big detour here. And you will never really find the shortcut here. But in this naive tree, what can happen is that you basically say, oh, I actually want to expand the root node again. And then I randomly sample an action that gets here. And then I'm already here. Right? So because you don't have the Voronoi bias, you don't keep necessarily these detours around. Okay, so that kind of just is kind of interesting, that a simpler method has this more powerful property. And just kind of what we said in pictures again, so let's assume we have this existing tree. We have this series of ball argument. We now already have also in the tree some solution that's close to the optimal solution that reaches a ball. And then because there's some non-zero probability of actually selecting this guy and not that guy, and a non-zero probability of randomly sampling an action that actually gets you from here to here, you get this probabilistic completeness and also asymptotic optimality. Okay, so if that's so awesome, why shouldn't we use it?
Because we have to explore really a lot of possible paths to find the optimal one. Like, this is just very small probability of finding this actual path.
Exactly. So it's extremely uninformative. Like, at least before with the Voronoi bias, we use this information on where's free space. And then also because of that, it has a high runtime and also high memory, because every single time you add stuff to the tree, and you need to keep it around for a long time. So in practice, I think this can't really solve anything that's interesting. If it does solve it, if you then look at kind of how close is the solution to the optimal solution, it's also very, very far away. Now, what is nice about it is that it has inspired another algorithm that is basically extending this idea and makes it useful. And that algorithm is called stable sparse trees, or SST star. And we will try to figure out where the name comes from, maybe after we discussed what it actually is. Okay. And it's also, like, again, another instance of this meta algorithm. So here we use something new for select nodes. So we use this best first selection, which we talk about in a second. For propagate, we still use Monte Carlo. And for the add connection, we actually use also like an extension that adds a little bit of pruning. And then in the paper, they also sold it as it's basically a naive random tree with a better selection and better pruning. Okay, so let's kind of look at these two things, like how does the selection work and how does the pruning work in a little bit more detail. Okay, so the selection, there's the pseudocode here, and maybe it's best if we also try to do it on using an example, just following the pseudocode. All right, so it basically says, so maybe I should start with some sort of tree first. Okay, so I have some tree, and now I randomly pick some node over here. And then what it says, so that's line 1. In line 2, it says, now I try to find all the nodes in my tree that are near to my random point within some delta, which is called this delta Bn, which is just a hyperparameter. And so let's assume for 1 second that this delta is pretty large. So I get something like that. So I have quite many kind of nodes, 1, 2, 3, 4, 5 in my tree. And then it says in line 3, okay, if that set is empty, I do something, so I don't care. But then in line 4, it talks about what I do here. So I basically return whatever has the lowest cost. So now I look at all the 5 ones I have. They're associated with some cost. And then I take the one with the lowest cost, which in this case, I assume is actually this one over here. Just because this one was the root node, this one should have the lowest cost. Of course, if the connection wouldn't have been like that, but like that, then the lowest one would have been here. Okay, and then the second case we have is if that radius is too small, so let's say somehow our radius is like that, then we end up in this condition in line 3, and then we just fall back to a regular nearest. So we basically just do whatever RRT does, which in this case would be that node here. Okay, and so we can already see here that it's kind of interesting. If we have this large radius, then we can really pick from many different nodes and try to prefer improving things with a low cost. If this radius is fairly small, then it more or less becomes the same as the naive random trees. Okay, so now we kind of discussed this best first selection. And then the next important change is that pruning step that basically decides, do we add something or not? And so in the pruning step, we need a new kind of set, which is called the witness set. And that has an interesting invariant. So first of all, what is a witness set? It is just a set of states from our configuration space. It's a helper data structure, so we don't necessarily do something with it. And then there's some fun invariant, as it says, for each of these elements or configurations in our witness set. There's only a single node in the search tree within some certain radius that represents kind of that state and has also the best path from the root node. So we have kind of two things here, at most one, and also lowest cost. Okay, so let's look at it maybe graphically. So let's assume we have some sort of search tree like that. Then if we have witnesses, then we can use this radius always as these kind of circles, and the witness points themselves are yellow. And you can already see that some of them are kind of identical to what's in the graph, but some of them are not. Like here, for example, it's not. But we can do this kind of little sanity check for the first property. This one has exactly kind of one node in the tree. This one has one. This one has one and it's itself. This one has one and it's also itself because this guy is slightly outside. This one has exactly one, and this one also has exactly one in the tree. So that is our invariant that we try to maintain while we grow our tree. Okay, and so maybe one big question is, how do we grow the tree then? Right, and so we will also look at that now. And there's kind of multiple cases, but they're actually not that difficult to think about. So the first case is that we didn't have a witness. So again, we have kind of our tree, and that's not the full tree, it's just kind of some part of it, so you can see that portions are cut out and they might be connected in parts that you can't see. But our property is still fulfilled here, right? So we have this witness here has exactly one in the tree, this witness here has another one in the tree. And then the one we want to expand was maybe this node, kind of in this direction. And in this case, there's no witness for this point because it's not inside one of these yellow circles. And so all what we do is we just add the connection and we make that new state also a new witness. Okay, so in the second case is, okay, let's assume we already have a witness. So in this case, again, let's say we expand this node, but we somehow want to go in this direction. Then we have kind of this potential thing. And this is a problem because now our invariance is violated. In particular, this witness over here has now suddenly two nodes that are in the tree. And that was not okay. So that's the old one, and that's the new one, and now we have to decide which one to keep. And there's kind of two cases for that, which are just based on the cost. So let's say that new thing is actually a lower cost, then we delete the old one. Or the other way around, the old one is the lower cost, and we just don't even add the new one. Okay, so what's the problem with this sort of updating of witness sets potentially? Deleting stuff?
XO could, of course, still be actually on the optimal path, and we don't know it yet.
Could it be on the optimal path? I don't think it. Maybe it could, but that's something we could also re-add it later if that happens. That's true.
Like we can't add it later, right? Because like it's like then we still run into the same problem. Like I mean, maybe it's.
If it happens to be at some point over there and lower costs, then we would add it again, right? But the idea is always we keep the one around that has the lowest cost. So if it had higher costs, it means it was not optimal, and then maybe later it will be re-added, but with a different kind of parent link, which is lower cost, and then the other one would be deleted.
But like in general, because we're in kinodynamic motion planning, isn't like also the exact position of the point relevant for any future expansions? And let's say my cost function for this old point will be very low to my goal because maybe I'll just go straight forward or something like that. And with my new point, maybe has a lower cost function up to that point, but then from there to go to the goal, maybe I have to do a turn whatsoever, and which will have a higher cost. Like what will happen in this scenario?
I agree. It's actually quite tricky. In these figures, it's still like the geometric case of SST, but in the kinodynamic case, you might lose some solutions that are needed. That highly depends on your dynamics. So if you have dynamics that really highly depend on the exact position, like let's say you have a narrow passage problem and you really exactly need to be in front of the narrow passage with straight wheels, then that can be an issue. I agree. But I mean something actually much simpler. So what can happen in not only trees, but any graph if you just randomly delete some stuff? Yeah?
If it's not an end node, we might have to separate.
Exactly. So things might just become disconnected. And that's a problem because then potentially we like throw away all the search effort. We like search for an hour, then we make a little mistake and kill one link at the beginning and suddenly everything is gone. So that's not great. And so because of that, there's this more or less interesting pruning, more advanced steps, it tries to avoid it. And to explain it, I also have these like example figures again, which is easier than the formal things. So let's say we have these three nodes, x1, x2, and then we just added maybe xa. And then now we also try to expand x1, and we get this x2 prime. And we have to like figure out which of the two do we want to keep, right? And so if x2 prime has a higher cost, it's easy, then we wouldn't add it. But if it has a lower cost, then it's kind of a potential problem. And so what we do here is that we also add, we have this active set, and we also add this sort of inactive set. And then we can mirror things over. So instead of really deleting x2 now, we just move x2 to our inactive set. So once we have it in our inactive set, we can remove it from our active set. And then that xa that was previously connected over x2 still remains actually in the active set, but there's this kind of link to the parent state that points to a node in the inactive set instead. So in other words, instead of letting the graph become disconnected, we don't really delete things, we keep it around as part of the parent node pointers. Okay, then how does it continue? So let's now assume we continue, and now we found an expansion that went from x2 prime and got into xb, and it's this part of the same witness set. So now we have the same violation that we had before with x2. So suddenly we have xa and xb as part of the same witness. Not allowed, we have to pick one of the two. Now the easy case would be that xb is sort of higher cost and we wouldn't have added the connection. But now let's assume xb is actually the lower cost and we have to get rid of xa. And that of course means xa gets removed, gets technically kind of added to the inactive set, but now because there's nothing really anymore in the inactive set where that x2 is needed, we can delete everything in the inactive set. And that also explains a little bit why the tree is called sparse, because it's not that we have to keep everything around. Like over time, we actually delete things that we believe are not really relevant anymore because they are higher costs than other solutions that we have found. Okay, and then the sparse stable trees has actually two nice properties. It's also basically probabilistically complete, and it's asymptotically near optimal. And so that's kind of a new term. And what it means is that it finds a solution with a cost of 1 plus epsilon. Epsilon is kind of a smallish positive number times the cost of the true optimal solution. Why is it now near optimal and not optimal? Yeah.
I would think that the size of these circles that we use for the witness sets kind of defines how granular our optimal solution is.
Exactly.
So if these circles would be small, the epsilon would be smaller, and if they're really large, the epsilon would be larger.
Exactly. And so in the extreme case, if we make the circles kind of zero, then we end up at the naive random trees. We would never do any of these fancy pruning stuff. And And on the other extreme, if we make it infinite, then we basically believe that the start state is in the goal region, and we would not even have to search, right? So there's certainly some sort of trade-off to make, and there's a relationship between this epsilon and these user-provided radii parameters. So you will also know upfront how high that epsilon is in principle. But of course, that's only true after infinite runtime. So you will never know if you stop it after an hour, how close you are to the solution. Okay. So what's this algorithm is actually quite good. It picks locally optimal. It has low memory footprint. The hyperparameter tuning is can be quite tricky actually. Like it's really something you have to play around with on a case-by-case basis. And also related to that, this near optimality is a bit annoying because this hyperparameter also defines indirectly your trade-off, right? Like on one hand, you want it to be high because then it can find things faster. On the other hand, it should also be kind of low so that you get closer to the optimal. Okay, then we explained sparse. What about stable? No idea, right? So I also had no idea. I tried to look at the paper. It's like that original paper is really short, maybe 8 pages. Just introduces the name, never explains anything. And then there's a journal paper that's, I don't know, 20, 30 pages. Has a long text and some idea.
Maybe is stable referring to the fact that we sort of don't throw away useful information, like that we keep this inactive set, so that if we scroll something and only because we find a locally better thing at one point, it turns out suboptimal in the long run, we don't discard that information.
Yeah, it's super related to that. So according to them, it was like mentioned on, I don't know, page 20 or something, inside some proof, that it comes from the cost kind of not going down. And that's super related to what you just said. So because we don't throw stuff away, we just always stably improve our solution cost. My guess is that they just wanted a cool acronym and then that's what they found in the dictionary.
2 letters just don't cut it.
Yeah, exactly. Already used for like search-based algorithms. The 1 letter and then, yeah, 2 letters are rarely used. Okay, any questions about SST? So we looked mostly at the geometric case. How does it work in the kinodynamic case? Yeah.
I would guess it's pretty similar, and we just do like with the algorithm before. We just like pick a point, but not set it randomly, but by using the kinetics.
Yeah, that's correct. So not only, what do we have? Not only similar, it basically stays identical. You had some comment?
Like, should these circles then sort of also be part of the actual state, like maybe velocity or direction in kinodynamic motion planning, so that we assign it a higher dimensionality? Because, like, let's say the problem again where I have to go in a specific direction, then if I only use my position, then I will maybe never find the actual solution because it will always get fooled away.
Correct. I think that's always, with the example, is also not so intuitive, but if you go for the, let's say, a car examples, and here everything was kind of in 2D, x and y. And then, like these things are circles. But in 3D, it would be kind of a sphere, right? But we can maybe still visualize it. But for the car example, maybe it would be like 4D or 5D or whatever. And then, I mean, you can't really imagine it anymore, but it's just a distance metric, and you stay within, like, you compare 2 points and make sure that the distance metric is smaller. But you would definitely include the derivatives in other parts of the state space, and your points become higher dimensional points. Yeah?
I also have a question, like, regarding dimensionality. Because with these curved lines, that hints to me at that we're basically like sampling in a subspace of the full state space, basically just like positions, and then maybe storing with them the current velocity, and just using that for like the forward propagation to a different position, but not actually sampling in the full state space that maybe also includes velocity. Is this something that you would implement like this, or would you actually, like, if you had a 2D car, would you include the two velocity dimensions also in the sampling in the search space?
Yeah, you include everything. So it's really like you sample like a 5-dimensional vector, for example, right? Like for a car, if you, I mean, it depends on the order of the car, right? But if it's a basic car, then it's just x, y, theta. Then you sample 3 dimensions. But if you have a second order thing where you also have velocities, then it's suddenly 5-dimensional. And you do sample that as part of your random, and it also is part of your distance metric. And typically there's some weights in the distance metric. So you take maybe the Euclidean distance of the position times the Euclidean distance of the velocity times 0.1. So basically the position part has a kind of a very high weight, and then the velocity part has kind of a pretty low weight. But the weight is mostly done to normalize the different components. Yeah, I feel I confused you more. I'm not sure.
No, I mean, I can feel like it could also be, like if I, for a 2D case, it could also be implemented that you just basically sample the new position and then propagate, because like these curves kind of like they come as a result of the dynamics, right?
Mm-hmm.
And in a space where the like one of the dimensions is basically the dynamics, it would kind of look like this, right? It would be, but I think we could do something like this by basically just sampling in a subspace that basically is just like x, y, but at these state points have like the additional information for the dynamics, and then just like propagating from that state point to a different x, y position, kind of, so that you always just, it's kind of a mix between like including the dynamics and not including the dynamics, but kind of just still in at somewhat geometrical, but it's not really applicable here.
Yeah, and I think it depends on what order of dynamics you have, because for higher order systems, you wouldn't get a valid solution, right? Like imagine like a car that is driving on a highway, and then you only sample the position. But it's already running at 100 kilometers per hour. And then you suddenly decide, oh, now I want to like maybe brake or whatever. That's going to be problematic. That's why we typically include all of the components, because we need to know, can we actually, for example, brake in time in order to make our exit. Okay, but going back to the kinodynamic case, actually nothing really changes. And the reason here is that we use this best first selection. So even in the kinodynamic case, I mean, we can always sample a point and then apply the thing to figure out which we want to expand. For propagate nodes, the same thing. And then because we have these witness sets, we don't really have this problem that we might have gaps between states that are within the same witness set. Because even if we delete one, we put it in this inactive set and we kind of keep around how we got there. So that's kind of like the magic trick here, is that in no part of the algorithm we actually need this direct connection between two states, right? Because we always just use forward propagation. Even if we replaced one thing, we just keep in our inactive sets the history how we got there instead of rewiring. Okay, so any more SST related questions? Yes?
Yeah, maybe I missed it, but how do we choose the points for the witness set?
Yes, so that kind of happens while you grow your tree. And so in that simple case, when there was no witness, it's really just the points that we just expanded to. And then over time, it might change because we kind of delete those points, right? Like we find something that's maybe in vicinity of this one, but over here and has lower cost. And that means we kind of delete this line here, but this will stay as a witness set. So in some sense, a witness set is just greedily what happens almost at the beginning during the expansion, a subset.
Okay, so each time we add a point outside of the witness set, we just add a witness
Exactly.
point. Okay.
Yep. Any other question? Okay, good. Then we will go to another really fun one, which has two letters. So that must be good. AOX, X can be replaced by many different things because it is a meta algorithm. So for example, X can be replaced by RRT, and then we have AORT. And so the input is any feasible kinodynamic planner, like kinodynamic RRT. And then the idea is that we put some stuff around and we make that kinodynamic planner not only probabilistically complete, but also asymptotic optimal. And that's where that AO comes from, just from asymptotic optimal. And so we have to just figure out kind of how we, what we put around the existing algorithms. And so the key idea is that we actually augment our configuration space and add another cost dimension. So if we have, let's say, our car dynamics with x, y, and theta, which is 3-dimensional, then we make it 4-dimensional, and the fourth dimension is the cost. At state 0, the cost would be 0. And then every time we expand, we also propagate kind of the cost forward and add the cost of whatever it is that action we picked, for example. Okay, and then what do we do with in this algorithm? So we basically has this meta algorithm that says, okay, the first thing we do is we just run our standard approach. So if we do AO-RRT, we just run RRT unchanged until we find any solution. If that doesn't have a solution, we are done. If it does have a solution, we can compute the cost of that solution. And we already know from like the last lecture, it's suboptimal. It's actually empirically very suboptimal. So like typically that cost is very far away from the optimum, the first one that you find. But it gives us some bound. So now we basically know that we can find a solution that has this cost or lower. And then we just repeat. So we say, now we run our algorithm, but we change it and we say our cost bound now is the cost bound that we have found. And we will never expand any nodes that have a higher cost than that. And then once we found a new solution, we update our cost bound again, and we repeat. So, very simple, right? Any questions about the procedure? Okay. Then we can maybe look at why it's asymptotically optimal. And for that, we need kind of two assumptions. So the first one is that this algorithm will terminate in finite time if some solution with a bound exists. And that's not too unreasonable for things like RRT, like standard kinodynamic RRT can do that. And then the second assumption is maybe less obvious, but we also need to assume that every time we run it with a new cost bound, that the new solutions that we get will actually be slightly better by some non-negligible amount. And so formally what you say is that the expectation of the cost of the solution in iteration y, given the cost bound that we gave it, minus the optimal cost, should be lower than 1 minus some omega, which is a positive number, times the cost bound minus the optimal solution. Yes, that looks a little bit complicated at first, but if you just put in some numbers, you can maybe convince yourself that it really makes sense. Like, let's assume your optimal cost is 100, and then your current cost bound is something like 500, so you need to be, then the difference would be 400, and then you want to make sure that you reduce it, for example, by, you multiply it by something like 99%, and then you get a smaller number. And then every iteration, you want it to go down like that. Okay? Good. And then to kind of show that it's asymptotically optimal, the idea is that we just introduce a random variable that tells us what is kind of this delta cost. So the cost or residual cost. So the cost of that iteration minus the optimal cost. And so ideally that delta would be 0, right? Because that means that we already found the optimal cost. Or it's positive, but it can never be negative by the definition of C star being the optimal cost. And then what we want to show is that these are random variables, so we want to show that the probability of this thing being greater than some epsilon value is 0 if our n goes to infinity. So if we kind of iterate infinite many times, then we want that this Sn basically converges to 0. This is just another, or that's actually the formal definition of probabilistic, of asymptotic optimality. Okay, and then the proof I will show, it's fairly short, but it uses like these two things. Like one is the Markov inequality, which I've just shown here, and the second one is the assumption that we already defined, just written now in the notation of the random variables. So the expectation of Sn given kind of the cost difference that I had in the previous iteration should be reduced every iteration by this non-negligible amount. And then it's just basically plugging in definitions. So we first use the definition of the expectation and the conditional expectation. So the expectation of Sn can also be written as the conditional expectation of Sn given Sn minus 1 times the probability of Sn minus 1, and we take the integral over it. Then we can use our little assumption that we had, that basically says, okay, every iteration that will get better, and we just replace this thing, this expectation over here, that we also have here on the left-hand side, with the thing on the right-hand side. So we get that here, and then we copy the rest. So we still have the probability, and we still have the integral. But because that was an inequality, this equal sign now also changes to the inequality. Now we have an integral. This omega is just some scalar value, so we can move it out of the integral, and the rest stays the same, right? So we just copied it again. And now if you look at this term over here, that is literally just the textbook definition of an expectation, and specifically the expectation of the solution in the, or the cost in the prior iteration. And then we can kind of apply it inductively. So if that is true in every iteration, then we can take the power here and start with the first iteration. Okay, and then the second step, we use now the Markov inequality. So I have written that down here again. So the first line is really just the Markov inequality. And then we simply replace this expectation over here with the value that we have found here. And we get this equation. And then the last step is really just taking the limit. So on both sides. And then because this omega is greater than 0, we actually get our desired result. Okay. So that's also something maybe to look at it slower if you couldn't follow at home, but it's really just standard steps under strong assumptions. Any questions about the proof? Okay, then what's nice about AOX is that it's really planar agnostic. So it kind of works for RRT is very commonly used. EST, which we haven't discussed yet, but we'll discuss later, is also very commonly used. It provides very strong guarantees. It's also very simple to implement in principle, right? Just these iterations. What's not so great is that if you do it kind of plainly like here, then you don't really use information between iterations. There is some small changes that you can do to reuse information, but it actually turns out that it doesn't necessarily improve convergence rate, at least. And the reason is that if you typically what reusing means is that you kind of just prune away parts of the trees that are high cost. But if you have this really kind of suboptimal thing right at the beginning in your tree, and you only prune away the rest and you keep this thing around, and then you keep growing that tree later on, it just doesn't get better. So surprisingly, actually in practice, it's even beneficial to throw stuff away, at least if you combine it with sampling-based planners. Either way, the convergence rate we can't really bound that easily. And practically speaking, it's kind of not so good. So it takes a really long time before we get to something that is close to the optimum. Okay, any questions about AOX? Good, then as promised, I will basically move this in 2 weeks, because there we will have some time. And instead maybe try to just have this lecture focus on kinodynamic motion planning. So today we learned about kinodynamic sampling-based motion planners. So in particular, RRT, SST, and AOX. We also learned about these naive random trees, but they're kind of impractical, even though they're nice. And so the properties were basically that kinodynamic RRT is probabilistic complete, but not asymptotically optimal. Naive random trees were PC and AO, but they're kind of too slow. And then sparse stable trees, they're probabilistically complete and asymptotically near optimal. And then AOX you can basically typically use with RRT, and then it becomes, it remains probabilistically complete, but it also becomes asymptotically optimal. EST we haven't really discussed yet, but that will come, as I said, in 2 weeks. And then next week, Andreas is going to give a lecture on the Open Motion Planning library, which is a library that is used both in academia, or it started in academia, but it's also now used in industrial settings. Even though it has this very generic name, it only supports sampling-based motion planners, but it's one of the most powerful solutions. And programming assignment 3 will actually ask you to repeat some of the things that you have done in programming assignment 2 with OMPL. So you will also get some hands-on knowledge on it. With that, I'm basically done with the lecture, and I wanted to say a few more things about programming assignments, since there were many questions. So the grading was kind of partially done, with some students happy, many unhappy. Then the teaching assistant went on vacation. She will be back today. And then all your potentially still unanswered questions will be either answered today, or there will be at least kind of an office hour announced where you can come and talk about your problems, if you have any, with the TA directly. I think like the most common issue was that people did a solution but didn't tag it. We typically find then with you tagging whatever you want us to grade, and then we grade again, as long as you don't tag something that you pushed after the deadline, because that would be unfair, but a tag is really just kind of a pointer to whatever you did. And otherwise, I think maybe one thing to keep in mind for assignment 2 is that the tests are now a little bit less involved, right? So in assignment 1, you really had very concrete examples, and the examples, we kind of checked if for these examples everything is correct in the continuous integration, and you should expect that if you got, if like all the tests pass, then kind of all the tests we run internally should also kind of pass. Programming assignment 2 is different. So there the test literally just checks that you write some stuff in the correct format, but there's no correctness check. So please come up with your own examples. That's kind of part of the assignment. Try to get a feeling for the algorithm that way by finding good examples. And then we don't test with hard cases. We test with very basic cases, so you should be fine for assignment 2. And moving forward with assignment 3 and 4, it will be kind of similar, right? So that continuous integration is there for us to mostly make sure that we can run our tests internally, not to give you an immediate grade. Yeah.
Can we add our own tests that will then also run in the CI?
In principle, yes. It will not affect your grade. If your tests run for several hours, you make everybody very unhappy. I mean, at some point I might configure something to kill long-running jobs if that becomes a problem, right? But right now we have basically one workstation that is configured sequentially. So, and we have about maybe 40 students or so, so they're actually enrolled, which also means if like everybody runs a CI for 1 hour, then it will take 40 hours to process everything. Any other questions? Either regarding this or also the assignment? Okay, then thank you very much.